Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn how to do speech tagging with PyTorch LSTM. What is speech tagging? Suppose you have a sequence of words, such as a sentence. For speech tagging, what it allows you to do is to classify each word in that sentence. In our example that we're going to do today will be, for example, classify words as either being a noun, a verb, or an adjective. Now, why do we want to do speech tagging? How is that helpful? Well, it's helpful in many natural language processing tasks, for example, creating new sentences. Suppose you want to generate new sentences that make sense, and we have ambiguous words, for example. Suppose you have the word right, which means, for example, right in like the direction, like go right, or for example, that's right, the expression, like that's correct. So right doesn't mean, can have more than one meaning. And speech tagging, if we know the classification for the word, we can create sentences that make sense and so on. So that's just a simple example for what you can use this for. It's also a very good learning example for LSTMs and recurrent neural networks. So how do we prepare the data? So first we import our resources. Here are our PyTorch modules that we need and Matplotlib if we want to plot something. Now, our training data will just create a very simple training data here manually. And it's going to be a sequence of words, a sentence, then their corresponding categories. So we have 3 categories here for our classes. So verb, noun, or just a determinant. So we have that, and here the way we're preparing the data in this example is we have a list of tuples, and we're splitting. We're turning the string all to lowercase, then splitting it into separate words, and then for each word we're assigning a category for that word. So this is just a toy data set. This is just a very simple example to see how it works. Now we need to create a dictionary that maps words to indices. Why? Because in a recurrent neural network, or an LSTM in this case, you can't just we don't just feed in the actual sentence in words. We deal with tensors, so we want a numerical representation of our data, which are words, which are sentences. So what we're doing is we're going to map words to indices. So for every unique word, there will be a corresponding index, and then we'll have index to word, and that's how we will map from one to another, from words to numerical. So we can do our training and get a prediction from our neural network, which only really deals with numerical values, with tensors of numerical values. So here for each sentence and tag in our training data, so each one, we're going to go through each one here. So for each sentence and tags, we're going to grab, so the word in the sentence. So we have a sentence here. Now for each word in that sentence, if the word is not already in our dictionary here that we define, our word to index dictionary, then that word is going to become the key in that dictionary, and then we're going to assign the corresponding index for that unique word. In this case, we're just grabbing the length of the actual dictionary, and initially it's 0, so it's 0, and then for each unique word it's going to be 1 and 2. So we have 0, 1, and 2 here, for example, and so on. For each unique word is going to keep increasing. So our key, so for our word to index dictionary, the key is our word, and the index is just a numerical value in an integer here. So let's actually go ahead and run these cells. And we're also creating a dictionary that maps the tags themselves to indices. So our classifications here, 3 possible values to indices. So each one has an integer value. So now let's actually go ahead and print out our dictionary that we just created. So from our simple training data that we have here, we see that we have all of the unique words, and each one has a corresponding integer index. So that's what we will use to map words to indices. So now here we want to import NumPy as well. And now here we have a helper function for converting a sequence of words to a tensor of numerical values, as we said, because for this, we're going to use it for training, as we said, because this is the format that we want. Our network will take in as input a tensor of numerical values. So here we have a simple function, prepare a sequence that takes in the actual sequence, and then a dictionary here to index. So we'll grab the indices here. So we're going to do a list comprehension. So we have a list. So for each word in the sequence that you passed in, we're going to grab the index. and then we're going to have a list for all those indices for every word in that sequence that we passed in. So remember, the word is the key. So the key, and then that gives us the indices. So we have our list of indices. Then we now turn it to a NumPy array. So we just do np numpy.array, pass in our Python list, and that'll give us our NumPy array. And then finally, because we want a PyTorch tensor, we're going to return torch.fromNumPy. So this creates a tensor out of a NumPy array, and we just pass the NumPy array that we created. So that's how we get our tensor of numerical values from the sentence, and using our dictionary. So now let's actually run this, and this is just an example here. So what happens? Suppose we feed in this sentence: the dog answers the phone, lower split, and then with a word to index dictionary, and we print it out. This is what we get. We get a PyTorch tensor, and these are the corresponding indices for those words that we get from our dictionary. Now the next step is to create our model. So our model will take in as input a sequence of words, as we said, in a form of a tensor, and we assume that these words come from a larger list of words that we already know. We call this a vocabulary, and we have a set of tags, as we said, for our classifications, our possible values. And now we want to predict a tag for each input word. So as we said, here's the structure. So for each word that comes in, so for example, the dog loves art, this is a sequence. For each word, we want to output a classification for that word. So what kind of word in that sentence that is. So here we have that. This is the structure. So the sequence comes in. And now we haven't talked about this layer right here, but I'll come to that in just a moment. So we have our LSTM, and we have our hidden state and our cell memory, as we learned in the previous tutorial. And each cell here is going to produce an output. We're going to flatten that output will be just a vector of class scores. So the way we'll grab the actual classification for our prediction will be from our vector of scores. We'll grab the one with the highest probability, the highest value. So we're going to be using a log softmax, as we did with image classification. It's the same idea but now we're dealing with a sequence, and we're outputting a classification for each element in that sequence. Now, what are these? And feel free to pause just to make sure that it makes sense, or do learn at your own pace. But here now, for the input, we can have any length of a sequence. Like, we don't know that the sentence will be 4 words in this case, for example. We don't know what it might be. So what we do is we add an embeddings layer, what we call word embeddings. And this embeddings layer will take in the size of our vocabulary and return a vector of a specified size. So whatever the length of the input is, this layer will return a vector, or actually a tensor, more generally speaking, a tensor of a specified size of embedding dimensions. It's a hyperparameter that we can pick, and we'll get to that in a moment. So that's how we can handle a dynamic or varying length here. We put this layer, word embeddings layer, before going into the LSTM cells here, so we can just handle variable sequence length. And we'll see how in code how that's working. So first here we'll create our class. We'll call it an M tagger. It inherits from an module, as is pretty standard in PyTorch neural network classes. And we'll define our init function, our constructor here for our LSTM tagger, and it's going to take in parameters of standard self, so the embedding dimensions, so the dimensions of the embeddings, so hyperparameter, then the hidden dimensions, so that's the dimensions of our LSTM, the size of our vocabulary, vocab size, and then the tag set size, so the size of our tags themselves, of the output vector. So here we call super, just pretty standard. Make sure we initialize the base class as well. And now we're going to start saving off our parameters here at the class level. So self.hidden dimensions, we're going to save the hidden dimension so now we're going to do self.word embeddings, and we're going to create here the layer itself, the embeddings layer. So PyTorch NN has this embedding class that represents an embedding layer that turns words into a vector of a specified size, as we said. So it takes in the vocabulary size, and then it's the shape, the output shape will be the embedding dimension, so the dimension that you picked here, that you passed in. Now the LSTM here takes an embedded word word vectors of a specified size as input. So out of the embeddings layer, now we have our self.lstm, save off our nn.lstm. Again, PyTorch has this LSTM class here and torch.nn. And we're going to, the shape coming into the LSTM is the embedding dimension. So here, whatever the dimension is coming out of the word embeddings is going to be the input dimension here for the LSTM. And then for the output will be the hidden dimensions, the actual dimension of the LSTM. That will be the actual output. So it's pretty consistent. And again, feel free to pause and also go back to the previous tutorial on recurrent neural networks to see how we chose that, how to think a little bit more about that. So we have our LSTM saved off. So now we need a linear layer when we call it here self.hidden2 tag. So we need an nn.linear again from pytorch.nn. We have our linear layers, which would be this layer after we get the output from the LSTM cells. And this will take in the hidden dimension. So whatever the output shape of our LSTM will be the input. And then we'll get for the second parameter here, the tag set size, because that's the size that we want for the actual vector of class scores, the output vector. And it's the tag set size. So in our case, it will be 3 because we only have three possible categories for the words in our sequences. So that's our linear layer. So we have our embedding layer, LSTM layer, and then our linear layer. And finally here we do self.hidden and then save off here a function here, which we call init hidden. So this initializes the hidden state. And normally, generally speaking, you want to initialize your learnable parameters in a certain way. So start of training, we initialize the hidden state. And remember here we have the hidden state, and we also have the cell memory. So we have that tuple. So we're going to initialize both of those learnable parameters, which are matrices. And here we're just initializing them with torch.zeros. And the access dimensions are so number of layers, batch size, and the hidden dimensions here, because again, hidden dimensions, you're inside your LSTM. So we have this function that initializes. So we save that off when we constructed an instance of our LSTM tagger network. And then we have a forward method for the forward pass of the network. So here it's going to take in, of course, our input tensor, the sequence of words. And here first we'll actually go ahead and create a word embedding. So we saved off our embeddings layer. So taking this input, we want to pass it into our word embeddings here, the sentence, and just convert it again. So we can deal with this because the length of this sentence might vary. So we want to be able to deal with that. So we have our embeds here. We save it, the output of our embeddings layer. And now we have our self.lstm. We have a forward method in for the LSTM. So here the output again will be the hidden, the self dot, so the output and the hidden state of our LSTM. So we get the output by passing the LSTM over our word embeddings. So here we need to reshape it to give it a batch size as well. So we're just doing here a batch size of 1. We have the length of the sentence, so that's the first dimension. Then the batch size, and then this -1 means just adjust to get whatever the rest happens to be here. So pretty standard in PyTorch. So embeds.view, reshape the tensor, make sure we have that batch size, and then here for the second. We have the self.hidden, so the hidden state here is a second. So here the first one is our reshaped tensor with the batch size, and then just our hidden state that we pass, and then we're going to get that hidden state back, right? Because here the output of an LSTM will be the input into the next, and so on, as we learned is the case with the recurrent neural networks. And we're going to do a self.hidden2 tag. So we're going to get our class scores for the most likely tag for our word, and we just reshape it here, remove that batch size that we don't need. So that's how we get the outputs. So that's our hidden2 tag for our linear layer. So linear layer, the shape is 1 dimension less here on that tensor. So we have our tag outputs, and now we want the actual scores. Now, we have our f, so from functional that we imported. So we have our log softmax function. We just pass in our tag outputs vector here, or again, generally speaking, a tensor we have tensor of different ranks. So tensor of rank 1, that's what we call a vector. So we have our tag outputs, and then we want this softmax along the first dimension 1. So the second dimension, the actual outputs. And now we just return the scores. We just return that from our forward method here on our tagger. So now, next, we're actually going to define how the model trains. So to train the model, we instantiate it as we just created it, and we actually going to define our loss function, which we're going to use this negative log likelihood loss because we're doing log softmax, pretty standard. And you see already a lot of similarities with image classification as we did before. And for our optimizer, we're just grabbing from optim. We're grabbing a stochastic gradient descent here, passing in the model parameters, and just a learning rate, which again is a hyperparameter that you can choose. And here we just do 0.1 in this simple example. So again, our LSTM tag, we're creating an instance of our class here. That's our model. And we just pick our embedding dimensions and our hidden dimensions. So the embedding dimension here is the size of the word vectors. Now for this simple vocabulary and training set, we will just keep both of these small. So we'll just arbitrarily hyperparameters here, just pick 6 and 6. So this will be the output shape of our embeddings layer, and which will be the input of our hidden layer, and then this will be the output of the hidden layer going into our linear layer, as we see here. So this is a very nice diagram to see. So we have that. We have our instance, we have our model, we have our loss function, we have our gradient descent optimizer. And now, prior to training our model, let's just see how it does on just a random test sentence here. And as you can see, prior to training, the actual prediction is just a tensor, and it just has ones. It just means it just hasn't learned anything. But we see the output how it is. So we have our tag scores here. So we have our test sentence. Then we prepare our sentence. You remember that function that we wrote to convert it to a PyTorch tensor of numerical values. We pass our word to index dictionary. So that is going to return the PyTorch tensor. And now we just pass that into our model, into the forward method here in our model, and it's going to return our tag scores here. So here we can see that tensor. So now we're going to get the maximum values for each one here, doing torch.max along the dimension 1, and here again we're just kind of seeing what we're dealing with here prior to training, just to see our objects, how they look like. So PyTorch tensors and the actual output predictions. So now we're going to train the model to get an actual prediction that makes sense. So this is what we're going to do, pretty standard. So loop through all of our training data for multiple epochs. Here we pick 300 epochs. It's a simple example, very simple data set, so it will run very quickly. Even without a GPU, even on a CPU, will be pretty fast. So we're going to prepare our model for training. First of all, zero the gradients, pretty standard. Then initialize the hidden state for our LSTM. Again, we have our initialize hidden in our model that we created in our class. And then, now this is an instance method here because we already have an instance of our model. Now prepare our data for training. So prepare sentence, our function, pass in our sentence here. In our training data, sentence tags on our training data. So pass in the sentence, convert it to a PyTorch tensor, and then our target. So what we actually want will be, again, we'll do the same thing, prepare the sentence, but now we're going to use this tag to index that we created instead of the other one. So we have two dictionaries here. So we have our tag to index, and we have also our word to index. So that's how we'll handle those mappings. So we have our input, and then we have our desired outputs, what we call the targets or the labels. And now we're going to go ahead and do our forward pass here. So on a forward pass on our inputs, and we're going to get our tag scores as an output. So we pass this sentence that's already been prepared as a tensor, and then our embeddings layer inside all that will take care of that, of converting it and all that, and give us an output of our tag scores. Now here we're going to compute the loss. So we have our loss function that we defined here. and we're going to pass in the tag scores and then the target. So it's going to come to compare the actual output values to what it should have gotten, to the ideal values, the labels, the targets, and we're going to get a loss. Now, so we're going to append our loss.item here just to grab the actual scalar value from the tensor and append it to our epoch loss here. And then we're going to do backpropagation. So we're going to backpropagate that loss, and then our gradient descent, we're going to do a gradient descent step. So again, very similar as we've done before, pretty standard. So let's go ahead and run this. And as you can see, it runs pretty fast for those 300 epochs, and the loss just keeps decreasing. So that's exactly what we want. We're printing out every 20 epochs here. So now let's go ahead, now that we have a trained model, let's go ahead and test. Let's see how it performs after training. So initially we saw it didn't do pretty well because it wasn't trained. So now let's go ahead and do, and so we have our test sentence here. The cheese loves the elephant. Again, just for learning and for testing here. So we have our inputs, same as before, prepare the sentence. Just convert it from words to numerical values, to a tensor of numerical values. And we have our tag scores here, which is the output of our model, pass in our inputs. And let's go ahead and print that out and let's see what we get. So now the values are different, the tag scores. And now once we pass it through our torch.max, once we grab the maximum value from this vector of predictions along the first dimension, along the categories, and we grab that, now we see that we get something that makes sense. So this is what we want. This is the for this test sentence, this is what we actually want. These are the actual labels for each word. So each word here corresponds to these. So loves is a verb, cheese, elephant are nouns, and these are just determinant words, right? Descriptive word like the, for example, will be this dead category. So this is what we wanted, and this is exactly what we got with our trained model. So yeah, so now we learn how to create an LSTM model for speech tagging with PyTorch. So thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.